So welcome to this second part of our journey into durability and availability in modern systems. So we have seen in the first part how to make data durable using recent hardware. And in this second part, we'll see how to make it durable when some problems related to the computer we are using to store the data happen. And in that case, we need to ensure redundancy in large scale to be sure that data survive. So this is this context, what is called today geo-replication. So you see the non-volatile memory DIM that are being scattered around, the France, but it can be at any scale. And this is a very common technique today to ensure high availability, despite, for instance, a data center is no more available, and to ensure the continuity of the service. So here we have like a simple schema of in which you have a client that is accessing some service that is being backed with some persistent storage, and it executes what we will call in the stalker command, that is an operation. And we have then some of the data replica. So a replica is a physical copy of a logical data item, okay? So you want to access, for instance, register something in your shopping cart, and we will replicate the item you're, for instance, buying at different location, and you have this command to access. Then we do some protocol to coordinate the data replica, and then we reply back to the client. So the problem we want to address is to have transparent, efficient geo-replication. Because when you are a programmer, you don't want to deal with replication of the data by hand. You want everything to be transparent, okay? And moreover, you want everything to be robust also. That is, if a failure occurs, such as, for instance, a data center is burning, the system automatically handles the failure or the unavailability of one machine or more in the data center, and allow the programmer to ignore that data is being replicated. And so for that, we're gonna look at various protocols that allows this. So the first approach for doing this that is being used in many systems today is called state machine replication. So it's an approach you see in protocols such as Paxos and Raft. And so the idea is that each of the replica has a log, okay? And in the log, in each position of the log, you store the command you want to execute. And you execute the commands in the order of the log, okay? So you go through your logs and you execute them, and you reply to the client. If, for instance, the client contacted you with a command, you store it in this replicated log and you reply to the client. To ensure that replica has the same command for each log entry, we use an abstraction that is called consensus. And this technique is used in many storage systems. So here I mark with a little plus when the operation is executed, and you can see that replica 1 is executing B, then A, and then C is pending. It has to be executed, whereas the others also advance in this sequence, but at a lower pace. And so replica 3 has not yet executed command B. And so this technique is used in systems such as Zookeeper, Spanner, and for instance, if you are using Kubernetes, the etcd storage system inside Kubernetes to maintain data consistency of the metadata consistency in Kubernetes is using that. Or at larger scale, you have also Apache Cassandra that is doing this. So this is what I will call in this talk classic SMR, classic state machine replication. So a key observation is that when you have operations, commands that are commuting, you don't need to execute them in this exact same order. So for instance, on the bottom right, we have 3 commands. Command A is setting 42 to item X, command Y is setting 7 to item Y, and Z is taking the sum of these two and storing it into item Z. Okay, so we can see that A and B are commuting, that is, you can execute them in any order. You will end up with the same state at the end. But they have to be ordered with respect to command C, okay? Because the result will not be the same if you execute first command C and then A, or A then C. Okay, they are non-commuting in a mathematical sense. So we need to take care of that. So the idea of what I will call in this talk generic state machine replication is that instead of a log, you have a partially ordered log. And in this partially ordered log, you have an ordering relation that says when you have 2 non-commuting commands, how to execute them, in which order to execute them. So for instance, going back to our 3 replicas, replica 1 has executed B, okay, but not yet A and C. Whereas replica 2, because the 2 commands are commuting, has already executed A, okay? B and A are commuting, so it is fine that replica 2 has already executed A. And we can see the interest here with this very simple example, is that the first replica has already executed B, whereas the other one has already executed in parallel another command. Okay, so this mechanism can improve fault tolerance. In the kind of most in the extreme case, everything is commuting, and in that case, you don't need to compute any order between the command, and it's boosts performance a lot. But in general, when you look at the application, you need to ensure the ordering for some of the data items that are being replicated. So a third class of protocol, and this is the class that we are going to look at in detail in this talk, is called leaderless state machine replication. So in that case, what we do is that we create a graph at each of the replica. And we ensure that the commands that are non-commuting are properly ordered in this graph. And I will come back to this a bit later. So the idea is that, for instance, we have chunks of the graph, and they are like, and replica are gathering those chunks, and locally the graph is growing. So for instance, in this example, you have this very same command as we had in the previous slide, okay, with the non-commutativity of B and C and A, C, but the commutativity of A and B. And so we have this chunk of the graph that are arriving, and we are increasing our knowledge and building up this graph. So for instance, replica 1 has 2 edges between B and C and A, C, whereas replica 2 has an edge from C and A, okay? And these edges don't, like, storing this what is called dependency relation. That is the ordering in which we must execute the command. So for instance, the edge, or the first edge between A and C, stores the fact that this edge stores the fact that A has a dependency with C, okay? And this top edge, these step edges, store that C has 2 dependencies between the operation B and E and A, okay? And oh, this is this thing, because you have a direct edge from C to A.
I have a related question. So why do you have so if you have a cycle, how you decide which?
Good question. Okay, this is answered in the next slide. Okay, so we have cycles. Effectively, as you have noticed, Gregory, we have cycles that can form. So for instance, in the previous slide, the relation that the dependency of A with C was not known so far at replica 1. But as the system progresses, eventually a replica 1 will know this information. And so we will have cycles. And what we do is that we execute operation according to the dependencies, in the sense that if a command has dependencies, we must execute those dependencies first. And if we have cycles, we break them deterministically. So the rule here is that we can execute the command once we know that it is transitively close in the graph, okay? We know the dependency of a command and the dependencies of these dependencies, etc. Once we have this information, we can break cycle arbitrarily and define an execution order. Does it answer? Yeah.
Isn't it determined by the application of the dependencies?
Yeah, so how we build up the graph, I'm going to explain it shortly. For the moment, it's just the intermediary abstraction we want to do. This is an intermediary abstraction in the sense that state machine replication is an intermediary abstraction. You don't know how it's being coded, implemented, whether it's Paxos, Raft, or whatever. What you see is just a log that is progressing the very same manner everywhere. Here, it's the same intermediary abstraction. You have this graph that is growing at each of the replica. Okay, so we have this leaderless state machine replication, and now we are going to see two important properties before delving into the detail of how to implement it. So there are two properties that every implementation must satisfy. The first property says that replica must agree on what are the dependencies of a command. Okay, this ensures that everybody is building the same graph. And the second thing is that because the graph stores the execution order, it must be the case that if two commands are non-commuting, we have a relations in the dependency graph, okay? So if x and y are non-commuting, we can have x as a dependency of y, we can have the converse case, or we can have also those two relations. As for instance, here with A and C, we have an example of cyclic dependencies, but we need at least one of them. Okay, so we have agreement somewhere. It's a distributed system. So this is a consensus box. We need a consensus box here to ensure agreement on the dependencies. Okay, so that's the two properties. We need the agreement with a consensus box, and then we need what we call a discovery service that ensure that the commands do not miss each other if they are non-commuting. Okay, so let's look at a protocol to do that. So one of the protocols that invented this idea is egalitarian Paxos, and it's a paper 10 years ago. And egalitarian Paxos is named like that because the idea is that you can make progress from any of the replica. You can build chunks of the graph from any of the replicas. And so in some sense, this is egalitarist in comparison to Paxos or Raft, where you have a single replica that order all of the consensus instances. At a very high level, the code of egalitarian Paxos works as follows. For each of the commands, you have a coordinator replica. In general, going back to the geo-distributed case, this is a replica that is closest to the application server. You ask this replica, okay, can you coordinate, please, this command for me? And the replica does the following steps. First, it contacts a fast quorum and asks, can you give me the dependencies, what you believe to be the dependencies of the command? And the replica returns all of the command it has seen so far that are conflicting with the command. So it returns this to the coordinator. So this is called a fast quorum or fast pass quorum. And the size of the fast pass quorum is this equation at the bottom with f the maximum number of failures. We'll come back to that later. And simply knows that it's a size of 2 processes in a tree system, 3-node system, and it's a size of 3 processes in a 5-node system. Okay, but it's governed by this equation. So if the fast pass replica is the fast quorum agree spontaneously on the same value, the same set of dependencies, we say that the command takes the fast pass. So in that case, the coordinator store the value that all of them agreed on spontaneously. They return all the same value in the graph. Okay. Otherwise, it do something else, and we come back to that shortly. And then it broadcasts this value, this set of dependencies. So in the base case, and I was saying that if everything commute, we can do very quick decision. We can enact very quick decision in leaderless state machine replication. This is the case here because we just have a back and forth with a quorum. So for instance, a closed quorum of replica. We just go back and forth with this closed quorum, and that's it. We are good. We can execute the command. However, you can have also collisions. So collisions occur when they disagree on what are the dependencies of the command. So in that case, and this is the else there, the third item, in that case, you take the union of all of the dependencies that were reported by the fast quorum, and you store it into a slow quorum. So you store it at a majority. Okay, at f+1 replicas, you say, okay, I store this thing so that if somebody look for the value, it will know it. And then once I have that, I go back to broadcasting the value of the dependencies, okay, of the command. So let's illustrate this thing with a timeline. So assume that command A is executed, is coordinated by the first replica R1. So here there is no concurrent command. So the replicas.or L2 and L3 answer it back saying, okay, I don't have anything as dependencies. So that's good. This is what is called a fast pass. And we know that the dependencies of the command A are empty. And we can broadcast the decision to everybody. So that's the happy pass. Now, assume that we have another command that is command B, which is being coordinated by the fifth replica. In that case, it contacts R3 and R4, asking them what are the dependencies. And we have a disagreement between them. The first one is saying A is a dependency of B because well, it received A previously. And the first one is saying, okay, I've seen nothing so far, so there is no dependencies. So in that case, we must go storing the union of the dependencies that are being returned by the fast pass quorum to a quorum of replica. And this is called the slow pass. So disagreement occur, we go to the slow pass and we store the union. In that case, the union is simply A is a dependency of command B. Okay, and once we have done it, we broadcast this information in the system saying, oh, this is a chunk of the graph. Just use it to execute the commands and update your data item. Is it good, or do you have questions so far? It's good?
So in this picture,
Yeah.
quorum is the same size as the slow quorum.
Absolutely, that's the same size. That's 3 replicas.
Okay. Just accidentally.
Well, it was designed on purpose, but accidentally, very true, it's the same size. Okay, so let's run this thing in a distributed system. So here it's a graph of an evaluation graph in which the authors of this egalitarian Paxos idea have tried to evaluate their system. So egalitarian Paxos is in orange, and you have 3 flavors of it. You have without any conflict, the 0%. You have with 2% of conflict, and then with 100% of conflict, okay? And then you have other protocols. So you have other leaderless protocol. One of them is called Mencius. You have Paxos, so the state machine replication approach, and then you have you have another protocol which is called generalized Paxos. This is also a protocol by the same author as Paxos, Landport, and you have two flavors of it. You have 0% and everything conflict. So we'll not dig into too much of the details of those results. There are several things to observe, but what I want to show you here is that the orange is very efficient when you have few conflict, okay? This is the most efficient of all of the protocols. So here we have where it's happening. So it's EU, it's London, Japan, Oregon, California, and Virginia. And so the protocol are deployed in this setting of 5 sites. So ePaxos is accessing three nodes, and you can see that it's the most efficient everywhere. But there is a but. When you have lots of conflict, the thing is falling apart, okay? Because it's less efficient than the blue one. And the blue one is like the very classical old approach, okay? It's used in etcd, everywhere it's used. And so it seems that it's problematic. You can win a lot, but as soon as you have conflict, so for instance, if you have auth items in a distribution of access, the auth item will have bad performance. So maybe you don't want to use it, okay? So you need to find a way to act this approach to do better than that. Okay, so this is another protocol, and one of the idea is to avoid disagreement, and so to avoid the problem of conflicting commands, okay? So we don't want to go through the slow path. We want to avoid the slow path. And the idea of this protocol that is called Atlas is that we're gonna make some assumption on the failures to ensure that if they are old, we can avoid the disagreement. And it is based on this notion of what is called a threshold union. So the threshold union is this operator with the union over a value, a cat threshold union. So it's UK, and it's defined over a bag of items. So in our case, the items will be the dependencies. And it's simply counting, you have a set of dependencies, and it simply counting the dependencies that are reported at least k times. Okay, so this is this equation there. If this is the set of y in E such that, this is the set of y, sorry, such that if you count y, you see it at least k time. Okay, k times. So for instance, if E consists of E1, E2, E3, and you have those set of dependencies, well, the one threshold union is reporting all of the commands, okay, because they are appearing at least one time, whereas the two threshold union is reporting all of the commands that are being reported 2 times. So there are 2 of them, A and C. Okay, so this is the cornerstone, the corner abstraction that is being used in the protocol. So it's simply returning commands that are enough there, and for some value of enough, which is k here. Okay. Okay, how we can use this cat threshold union operator? We are going to change the fast pass in egalitarian Paxos. So in egalitarian Paxos, we have this condition to say that the spontaneous agreement occur. The condition is that in the quorum, the fastpass quorum, everybody agrees on the same dependency. So this is written there. We take the fastpass only if for any 2 replica in the fastpass quorum, they report the same dependencies. Okay, this is the condition. And what we do is that we change it by like more versatile condition, which says that if the command is reported at least f times, okay, we can take the fast pass. And f is the number of failures. So the idea there is that if a command is reported at least f time, we will know what is the fast path that has been taken by the coordinator if it fails. Because we just gather some quorum of size q minus f minus 1. Okay, so the size of the fastpass quorum minus f minus 1. And those replica, they know what was used for the fastpass. Because if the fastpass is taken, then everything that is being reported, so everything in the union of all of the dependencies reported by the replicas, or in its F threshold union. Okay, so everything that is in the dependencies that are being reported by the replicas appears at least F time. So if the coordinator fails, I can ask the remaining replicas to give me back what was taken as the dependencies of the command. Okay, this is the idea. We change the fastpass condition of egalitarian in Paxos with this condition that is that has as parameters the number of failures we want to tolerate. Okay. So this is the key idea of Atlas, and it works well. So let's see first an example. So for instance, it's f equal 1. We go back to this example where we had to take the slow path in egalitarian Paxos. Remember, there was two processes, two replicas, R3 and R4, proposing different dependencies, and we took the slow path because, well, there was a disagreement here. If we have f equal 1, every dependency that is reporting at least one time, which is vacuously true, is in the union, so we are good. So we can always take the fast path. So in this case, we don't need to go through the slow path, and we can directly go to broadcasting the dependency of the command. So in that case, we avoid to go to the slow path. So the parameter is the number of failures, and the thing is that in practice, this is making sense. We can consider a small number of failures in a geo-distributed system. And to evaluate that, there is this experiment backing the protocol assumptions, and which measures the time. If you take your timeout, okay, and you wait for and you execute a simple ping between different sites, namely here it's 13 sites, and you wait a certain timeout before considering the sites slow, you count the number of timeouts you see globally in the system. And so the experiment is being executed during 3 months, where at 13 sites in Google Cloud platform, the machines are pinging each other, and you count the number of times you have a failure, a joint failures. Okay, and you can see that it makes sense to have small amount of failures, at least from the perspective of link failure. And because you have this thing, in this very experiment, the number of failures was at most 1. You can make the assumption that when you are of uncorrelated failures, you can consider a small number for f. Okay, so for instance, Google is reporting to use f equal 2. Consider that you have at most 2 failures, one unplanned and one planned, when they're using Google Spanner for data replication across the US, or the service is available, in fact, for everybody today. So in general, you can assume at most f equal 2. So this makes sense to consider a small number of failures. So in this case, where you have a single failure, in practice, it's kind of rare, because you will always have an unplanned failure. So, but this is just for the purpose of the presentation, to see you can take the fast pass at every time when you have f equal 1, but f equal 2 makes sense in practice. Okay, so this is the Atlas algorithm. Simply change the fast pass through, with this cat threshold union-based fastpass, and you have the algorithm. So is it worthy to do this change? And this is an evaluation in which you have Paxos, egal in Paxos, the Mencius algorithm that was there previously, as well as two algorithms that are variation of Paxos that are using also the assumption that if there are few failures, I can do better in Paxos, and they are compared to an optimal, a theoretical optimal, and also Atlas in two versions, first f equal 1 and f equal 2. And you can see that indeed the amount of conflict in this graph is 2%. You can see that the protocol is way faster than the other approaches. And this is the case for large-scale deployment. When you have large number of nodes, for instance, in this case, they are like scattered around the world. Okay, so we have found a way to deal with contention using this idea of avoiding the slow path. Everything looks good. There is still a problem, which is the tail latency. So if you look at the average, everything is fantastic. You have a good average. The problem is that the average is just one metric, okay? In the distribution, you take the average or the median. But if you look at the details, you want also to have good performance in the tail of the distribution. And unfortunately, those leaderless protocols, they have bad performance when you look at the distribution. So here we have a plot in which we consider egalitarian Paxos with different type of conflict rate, so different amount of conflicts. Okay, so with 0%, the protocol is impeccable. It's very efficient, so it's there. It's the green line. It's the green line. Okay, so it's way more efficient than, for instance, Paxos or Mencius. But as soon as we are adding more conflict, the tail latency is degrading. And if we zoom into the protocol, what is happening is that it's very degrading. That is, if you look at the last percentage, you will see that the time it takes for a command to execute, it's in the order of seconds. And Atlas has the same problem. So tail latency is an issue, is a concern in this family of protocol. So we need to find a solution to fix that. So for the purpose of just in the worst case, but also as an illustration to see as a point of comparison with the next protocol, I've depicted here a graph in which you can see that why there is a problem. So in this graph, we have a chain of dependency that is being formed. That is, we have a command, namely the blue command, the red command at the top is executing, and then it's picking up the blue command as a dependency, okay, which itself pick up the green command, okay, and this command is picking the purple command, etc., etc. And this forms this chain. And if you look at what is happening inside those protocols, this graph-based protocol, you will see a very long chain, thousands to tens of thousands of elements in it. Some of them have inner chain, like small cycle in them, but others are just like very long, and it impacts latency and explain why the end of the distribution is showing this effect. So this is the underlying reason, because you're doing everything in the decentralized manner. You end up with these chains forming. So we need to solve that. And this is the approach of Tempo, which is proposing to solve this problem by agreeing not on a chunk of a graph, but instead on a timestamp. Okay, so the idea is to have timestamp computation. So much like other leaderless protocol, you compute at each of the replica a timestamp, okay, in a distributed manner. And then you have a second phase in which you wait for the timestamp to be stable. That is, you know that no more command with lower timestamp will be submitted. Okay. So here I have displayed the fast pass condition of tempo. So it's very similar to the one of Atlas. In fact, it's a follow-up work, except that you don't use dependencies, but instead you use timestamp. So you take the fast pass when you know that the maximum timestamp that is being reported, so it's the same protocol as egalitarian Paxos. You send the command to a quorum, the quorum reply, except they don't reply dependencies this time, but they reply timestamp. And you take the fast pass if the highest command, timestamp was reported at least f time. Okay, so it's kind of the same operator. It's a threshold union operator, except that the lattice was a set of sets in the previous one, and here it's integered. Okay, but that's the same idea. So if we switch this thing, if we switch the computation of dependencies, swap it with timestamp, we can have this run, for instance, if we go back to the example previously. So here we send command B, and because R3 has already seen A, it will return 2 to node 5, to the fifth replica. And if we consider f equal 1, we know that it has been reported at least one time. So we take, again, the fast pass with command B and sending that, well, the timestamp for B is 2. Okay, so it's the same idea in spirit as Atlas, except you use timestamp instead of dependencies. Okay, and then there is the agreement on the dependencies, but it's not sufficient, okay? Because I said you need two things. First, you need to agree on the timestamp in which you will, the order in which you will execute a command, but then you need to wait stability. And stability means that you know all of the commands that can have a lower timestamp. You know all of them locally. So to do this stability thing, what you execute at each replica is the following. So first, you need to agree on the timestamp, and then you need also to know all of the commands that have a lower timestamp. Okay, and to be to know this this second point, that are the commands that have a lower timestamp. Replicas in this protocol in Tempo are sending promises. So promises indicate what was your proposal of timestamp when you were contacted by the coordinator of that command. Okay. So for instance, locally you can have a table like that. So you know that replica 1 sent the promise at h2 a that is 1. And then replica 2 sent 2 for C and 1 for A, etc., etc. And once you know a quorum has reported promises that are higher than the timestamp of the command, you know that the command is stable. Okay. So in that case, you can execute them, and you execute a command in the order of the timestamp, breaking ties arbitrarily. So for instance, A and B here, they can execute, which is marked with this underline sign. So they can execute two of them. And if you consider that there is a canonical order such that A is lower than B, you execute them in the order AB. Okay, so you need two things. First, stability, first agreement, consensus again on the timestamp, and then you need this stability mechanism. And in Tempo, it's in the background, in the sense that you run it not in the critical path, time to time, and you construct this table of promise. And once you know that a command is stable, you can execute it together with the command that have to be ordered before. Okay, you don't have to execute each command every time. You can do them by batch. It might be more efficient. Okay, so you need this this table. So let's go back to our example. You remember I was explaining with this example that there is state latency in dependency-based leaderless state machine replication. So the protocol is supposed to solve this problem, okay? Because that's an illustration of the problem. So let's see how Tempo does so. So here we have the table of the promises that are being built along the execution, because you know in the background what are the promises that each of the replica sent. There are also gray boxes in the table. This indicates that you skip some of the timestamp, what is called in Tempo detached promises, because you did not assign the promise to the command to anything. So, for instance, here you have a gap here in replica 1, because command D is proposed with a timestamp of 3 by replica 3, because it only knows that there were 2 commands, okay? So one, he was proposing 1, then 2, and then he proposed 3. So, no, sorry, it's replica 1. So, yeah, this guy received a command that started at 3, so because it's the first command by emitted or received by replica 3, so there is a gap here, and it skips attaching the command, the promise to any command. So in this example, we can fulfill the table again, similarly. And what we see is that quickly the command are being executed so solving the problem we were seeing previously, that is, you have a long chain of commands. So here, namely, we have the command A can execute, then B and C. Once you know that a quorum has reached, so for instance, if you have the chunk of this table, you can execute A. Once you know that B, which has a lower timestamp for the moment, is you know the timestamp of B, that's good. In fact, you need to wait ABC, because when you know the timestamp of B, B has to wait C, and no, well, in fact, A is lower than B, so in fact you can execute. You need to wait B. Sorry, you need to wait B to agree on B, and once you know B, you can execute A right away, because you have a quorum whose promises have passed the timestamp of A. So you know that everything that could have a lower timestamp is known locally. So this explains how Tempo is solving this chain of dependencies and does not exhibit this problem. So if we look in detail, like of this thing in practice, this thing, we can observe that the tail latency of Tempo is way better than the one of Paxos I was presenting, and Atlas also, for comparable value of F, and also of another protocol called Caesar I did not describe. So it improved the tail latency of leaderless state machine replication. Okay, so do you have any question? There are exercises that are coming, so if you have questions regarding, but they will also maybe clarify your understanding. Okay, so we have some exercises to manipulate a bit the notions I was presenting and see if you have grasped some of the concepts. Okay, so the first question is about the performance of Paxos versus egalitarian Paxos on the Californian side. Okay, so the question is, Paxos is as fast as Paxos. Can you explain why? Yeah.
I can guess that maybe in this case, when there are more context, they are basically the same.
You know Paxos or not? I'm making this assumption, which is people know a little bit state machine implication. So, so Paxos is leader based, in fact. So, okay, maybe yeah.
Maybe it is because when there are no conflicts in Paxos, it means the same thing as if there is only one single leader in regular Paxos.
Yeah.
Because it suggests everyone with.
Absolutely, that's the answer. So California is the leader site in Paxos. So Paxos, you have a leader that is coordinating the replication, okay? And it's storing at a quorum of replica the next command to execute, and then it returns the answer. So all of the clients that are co-located with the leader, they have the best performance possible, okay? That's why you just have a back and forth to the closest quorum. So that's why you have the same performance as egalitarian Paxos. That's correct. Okay. Next question. So on slide 59, the optimum is the latency to reach the closest majority quorum. Why and under which assumption this makes sense? So in this slide, the black line is the majority, is the closest majority quorum. Why this makes sense and under which assumption? Yes.
Maybe the more efficacy you have, you choose like the fastest. The more efficacy you have, the more the subset, like the more the latencies of fastest subset like come lower and lower.
So this is the fastest quorum. So subsets, which is a majority. Okay. So why do we consider it's the optimum you can do in a replication in system? That's the question. Why is it you can't beat this black bar? And under which assumption is it true? It's a two-part question. Okay, do you know the cap theorem? Okay, maybe I should have started. Yeah, so please. Yeah. Okay. Partition tolerance, right. Okay. Exactly. Exactly. Yes. You need to reach a majority. Okay? You're bound under cap. You need to reach a majority. So why this is the cap theorem? And under which assumption is it an optimum? Why is it optimum? What are the assumptions that make it optimum?
That the failures are rare and to delay more than a half of requests, you would have to have like a lot of slow nodes.
Maybe I did not understood. You need, if you don't, you need to delay some requests. That's your point. If you're not optimal.
I mean, if you have like more nodes and there is probability that some of that some concrete node, one of those is like slow. As more nodes you have, the probability that the bottom is slow is like.
This is optimum in the case where you have the same distribution of failures everywhere. Okay, so there is, yeah, you're right that adding more nodes may create more failures. That's true, but well, it's independent of the latency of the system. I mean, it's you're making the assumption that yeah, I mean, you need to contact a majority. That's it. But the thing is that we take the latency at the closest quorum for each of the replica. So it makes sense in the circumstance, under the circumstance, which is that they are all equal. Okay, it's a fairness assumption. You want optimum everywhere. That's the assumption. Okay, because I can have, for instance, with f equal 1, I can have those two, like if I have, for instance, a 5-node system like this one, I can have, since f equal 1, I can use those 3 nodes to do Paxos, and the other one will reach the Paxos node, okay? So this node, the leader, will be super efficient, for instance, but the other one we have to route through it, okay? So the assumption that we want fair performance everywhere ensure that you cannot beat the fact you need to contact a majority. It's not possible by cap. So cap tells you it's optimal. It's with the assumption that you're fair. If you consider fair performance, that is, everybody has this has his optimum value. Okay, so let's go with the fourth question. So in Atlas, how to recover a command when the coordinator has failed? Assume f greater than 1. Oh, it's not the right. Yeah, strange. Yeah, that's it. Okay, so in Atlas, we have this fast pass thing, okay? How we recover if there is a failure? There is this idea here that says, if the coordinator fail, we can save the day. But I did not explain why. Why is it actually working? How can you continue the protocol? I only explained the good cases in the presentation. But assume the coordinator fail, f is greater than 1, how you continue, how you implement the protocol in this good case, f greater than 1. What can you do? Yeah, you ask the q minus f minus 1, okay? Take the union, okay, and then what you do? Sorry? So you have the union, okay? So you're sure that you know that the coordinator has failed, okay? It's a corner case, like it's a good case. You know there is a failure of the coordinator. So you ask the fast quorum, okay, minus f minus 1, okay? So q minus f plus 1. And you take the union, and you know this is the good value, right? Okay. Yeah. So, okay, that works. Actually, the thing is that so you just have to broadcast this value, and this is the dependency. The thing is that you need to store it. Okay, that was the question, is just you need to store it. Okay, you cannot broadcast it right away. You need to store it. And this is in the case the coordinator has contacted enough replica, okay? Otherwise, you will need to do the first step of the protocol, and you need a consensus box at the end of the day to make the agreement on the dependency. But in the good case where the coordinator has failed and managed to reach everybody, you can just leave with this value because you know it's the fastpass value. But if it has failed before contacting everybody, you need first to do a phase. So you figure this out by contacting those nodes, q minus f plus 1, okay? And so if all of them have been contacted by the coordinator, you're good, okay? Because that's what is there. But if some of them have not, what you need to do is take the union and write it into a consensus box, okay? You have to make it, you have to ensure there is an agreement between the replicas on the same value of the dependencies. So the first part is correct. That is, if we know that everybody has received something from the leader, we are good. We can take the union and that's it. But in the bad case where the coordinator has not managed to contact everybody, you need to store it in an agreement box, okay? So you can use one-shot consensus, like Paxos or whatever you want, but you need this second part of the protocol. Okay, good. So there is a bonus question. It's a tricky one, which is the case f equal 1. We can ignore it for the moment. Okay, now the fourth question, it's about tempo. And why do you need to wait for a quorum of high enough promises before executing this first item? So I can execute a command once it's stable. It's stable when, well, I have an agreement on the timestamp, and I know that every command that I know locally, the timestamp is agreed, okay? So for instance, if I am here at R4, the command is not stable due to the second item because I don't have an agreement on the timestamp of C, okay? It's not known for the moment. What is because you just have two nodes that have been contacted so far, so I'm not aware of what is the agreed command, the agreed timestamp, okay? So I need to wait. That's the first two conditions. Why do I need the first? Why do I need that the quorum, a majority quorum, has reported promises that are above T? Why do I need this third condition? Why can't I just have the first two and that's it, I execute? Why do you need this third one? So you can provide a counterexample. That's fine. Yes.
Is it because that ensures he has the complete wisdom? It's like he knows.
What do you mean by complete? Right. New promises might change the situation. I agree. So in this example, for instance, let's say you see only this part, okay? So we have 1 and 2. You agree? We have 1 and 2. We have timestamp agreed for A. Oh, okay. No, sorry, it's this way. We have timestamp agreed for A. We have a timestamp agreed for B. And A is lower than B. So we can execute A, okay? If we throw away, no, sorry. Yeah, let's again this thing. So we have this part, assume the rest is blank. So you have A, you have B, and assume you know that B has a timestamp equal to 2 and A is lower than B, okay? So in that case, you don't use, let's say we don't need 3. We could execute A, but the thing is that if we don't consider this thing, we don't have enough information because C can also have a timestamp equal to 2, but B with an identifier lower than A. And in that case, you have an extension of the protocol. You have a continuation of this run in which C is executed before, okay? So the order, the canonical order here plays in favor of A. if it's it's a lexicographic order. But if it's another order, we don't know if C can end up with a different, the same timestamp as A, and in the lexicographical order be lower. Okay, so when you know a quorum, you know all of the commands that can have eventually a lower timestamp than the one of the command you want to execute. You want to be stable. So that's why you need item 3. Okay, is it clear? Mask this thing. Consider that C has a lower identifier in the lexicographical order than A. Consider that A and B have timestamp 2. A is lower than B, so far so good. We can execute A. But the problem is that if C end up with the same timestamp 2 as A and B in a lexicographical order lower than A, then it can eventually end up being executed. Okay, that's why you need this third item to reach a quorum of the replicas. Okay, so that's it. That's the exercises, and the end of my lecture. So thank you very much for your attention. If you have questions, I'm glad to answer them. Otherwise, we can have a break. Yes, Petr.
What would you say about these recent protocols based on DAGs, background,
Yeah.
replace all these applications?
Interesting. So DAGs, are they leaderless? Okay, so one interesting thing is that leaderless state machine replication has at its core the fact that you are leveraging commutativity. Okay, in the abstraction there, I gave you there with the two properties, you have this thing. Of course, if you want to consider everything non-commuting, that's good. And in that case, this would work. The difference is that with, like, for instance, DagRider and others follow-up like Narwhal, etc., is that they compute a sequence, which is different than this abstraction in the sense that you are building a total order. But if you consider that you don't have to be genuine, okay, you could consider them as leaderless. So this poses the question of what is leaderlessness? Okay, which is something I did not answer in the talk, which is an interesting question. So, for instance, in the leaderless consensus paper of Gary, they propose a definition of it, but it's interesting. I mean, here the idea is to grasp it with the decomposition of the protocol. The idea is that you can make progress in the sense that you don't need one of the nodes to be necessary in the order. You could consider that to define it as you can use any quorum to make progress. So in that case, they are leaderless indeed. The thing is that they don't leverage commutativity. Maybe that would be interesting to have variation of them doing that. And of course, they are BFT, which is not the class of protocol I have presented. That is, they'll support arbitrary failure. But to me, they are really leaderless protocols, absolutely, even if they don't consider the commutativity of operations. So they could be, in some sense, described in the same manner by composition. What is super interesting, of course, and amazing in this protocol is they do agreement locally. That is the consensus box inner property of the graph. And that's fascinating. And yeah, it's a very, very interesting class of protocol. Now, performance-wise, it's another story. And yeah. Yes. Yes, you don't. There are additional problems that are for instance, reliable broadcasts, which is used at. I mean, if you look just at DagRider has a kind of very high latency. It's 12 message delays if you put a rara broadcast in it. So they have the successive iteration, they improve it. I think the latest one is the CSS paper, and it's for message delay, and maybe they have even an archive paper which is even faster. I think the delay matter a lot in the sense that you want the application to receive even if it's a blockchain application, you need a faster answer. Of course, throughput is also important in the sense that you can pipeline operation a lot. And if you have write operations that do not have return value, what matters most is throughput. Now, as soon as you want to see to have a return value of the operation, latency matters. It depends on the application. So, yeah. Yeah, please.
Show the comparison slide of Paxos.
Atlas Paxos. You mean this one, right?
Here, to understand correctly, that what f equals 100 equals 2 is f is the maximum number of failures, right?
So this is the maximum number of failures the system can tolerate.
So,
Concurrent, of course.
yeah, it's like typically you rather set the number of failures, and then from that you set the number of replicas to be.
Yes, absolutely. Okay, that's an interesting question. So what is the use case for that? 13. Okay, so the thing is that you can have many replicas. Like going back to the previous question, blockchain is one example of it. You have plenty of replicas, but maybe there are a few Byzantine in them. You don't need to have f lower than a third of them. You can have f equal, 10. You see? So you're interested into weakening the adversary to improve performance. That's exactly the idea there, the approach, except that we're on the crash failure case. We are not in the BFT case.
So it's just that. Okay, I see what you mean.
It's slightly more fair to compare by the number of failures rather than the number of replicas.
The thing is, you really want those 13 sites.
Yeah.
You see, you want to have, and this is the question at the end of the first, second question of the exercise. Under which assumption is it optimal? Actually, we want fairness, fair treatment everywhere. We want to have fast operation everywhere. We don't want to route everything through a Paxos box. You see, so we want fast and replica everywhere, and fast operation everywhere. You see, so that's why. Optimal is the latency to the closest majority quorum. And this is optimal when you consider that everybody has a fair treatment, that they need to be the fastest. I mean, the optimality is not a function of the site. And by cap, you need to contact the majority, and then it's the closest. That's why. Otherwise, you can have this box, but latency is bad if you are nearby.
Sorry, but since we have a few minutes, can you walk us through again this Atlas product?
Sure, of course, with pleasure. Okay, is it good, the cat threshold operator, cat threshold union? You take what is reported at least k times, sorry. Okay, and then this is the fastpass condition of egalitarian Paxos. Everybody in the fastpass returns the same value. Okay, so you take the fastpass if you're sure this thing, and we swap it with this condition that says the union of the dependencies that are being reported, or each of those dependencies is reported at least f times. If we have that, we are good. We can take the fast pass.
Really great if you have like concrete examples.
Okay. Yeah, so let's go back to that. So here we have f equal 1. We report A by R3 and nothing by R4. And we take the union, and the union, if f equal 1, of course, everything is reported one time. So we can take the fast path. Okay?
If it was one, still you use the smallest optimal or right?
Absolutely, yes. So the explanation for this, and this is the purpose of the third exercise that says, why is it correct with f greater than 1? And the case f equal 1 is a bit tricky. I can explain it if you want. With f greater than 1, the idea is simple. It's just that you can ask do the replica, take the union, and because with f greater than 1, you are at least in a majority, you are sure that what you take is if there is another command, you have seen it because you go to a majority. With f equal 1, it's a tricky case. I can dig into it. Yes?
Like in this example, what's the order? What's the total order of A?
A is before B.
But how come, what if we slightly change the example so
Yeah.
that A sees B and B sees A,
Right.
see each other?
Yeah.
Like how can we tell these two situations?
They see each other. You mean there is a cycle then?
Yeah.
Yeah, in that case, for instance, let's say we have f equal 2 and we contact 4 nodes, right? Except that the order is swapped between those 2 nodes. For instance, that's a possibility. In that case, you need to wait, and you see that. I mean, it's not changing at all the logic of Paxos. That is, you construct a graph and you execute according to the graph in the same manner as egalitarian Paxos.
So we cannot execute B until we also.
Yes, if there is a cycle, you need you need transitive closure in the cycle in the graph. So to convince about the case k equal 1. So the thing is that when you're sending also the dependencies at the leader. So everything that is being reported is a superset of what the leader is sending, okay? So what happens is that if there is one failure, you know that by contacting 2 nodes, you either have the leader in it, and in that case, this guy knows whether he takes the fast path or not, so you're good. Otherwise, you have those 2 nodes, and you have also the union of what the leader decided as the fast path.
Reported means that you receive it from some other replica.
Yeah. Yeah, reported means this message.
Which is not you.
You take the union here. It includes what the leader is sending. So you take the union, and when you are recovering because there is a failure, or you know a part of the graph, there is a pending command in it, and you have to like execute things. So you do a recovery, what is called a recovery. That is, you take over, like in Paxos commit, you take over one of the consensus instance to decide what it has to. Then in that case, first before going to consensus, you ask those q minus f plus 1 nodes, which are actually 2 here. And either you have the coordinator in it, which will tell you whether it went to the fast path, and in which case, which value it took. Otherwise, you have 2 nodes, and the union of them, you have everything minus the coordinator. And as everything includes what the coordinator has as its dependencies, you have the exact same value as what it took for as a fast path. So this ensures that the agreement, you ensure you go to consensus with the very same value. Okay, maybe I intentionally did not describe the consensus part because it's for understandability purposes, because otherwise, I mean, I did not want to explain the recovery part because it's tricky. That's why the talk is not about recovery too much. It's just about how to refine the algorithm to be better in the common case, because the recovery case is subtle. But for f greater than 1, it's kind of simple in the sense that everything is reported by a majority, so that's good.
Sounds like a tautology to me when you say everything which is reported should be reported at least once.
Yes, it's a tautology. You always go to the fast path. That's very true. That's the property of the protocol. It's a bit amazing, but that's the case, yes, actually. So the thing is that what you're sent here as dependencies by the leader, they're sent back at least, plus the additional dependencies of those nodes, of the replicas. Okay? And then, if you have f greater than 1, you're sure that if you take a majority inside this fast quorum, okay, you have intersection between two majorities. So you know that commands will see each other, okay? And you retrieve the result of the fast pass because everything is reported at least f time. So if you ask everybody q minus f plus 1, you will have all of the dependencies of the fast pass, okay? Because there are at least f minus 1 time, okay?
So you only have the fast path in one failure.
Yeah.
Essentially, in both three cases, one failure is the same components.
No. Because if you have a failure, you need to recover. So for instance, okay, assume that this is failing, this part, okay? Because the first replica has failed. You need to know what are the dependencies of A, okay? You're just there, you computed that A is a dependency of B, so you need to execute B, and you need the dependency of A. So you do this recovery thing. So the recovery thing is that you go asking Q minus F minus 1 processes minus plus 1, okay, and Q minus F plus 1 processes in the fast pass what are the dependencies you reported to the leader. And because what the leader took as a fast pass is at least reported F time, those Q minus F plus 1, they have everything, you see? And then you take this value, and in the recovery, you go to a consensus, which is kind of a black box. You say, okay, that's the dependency of the command. Does it make sense more now or not? Okay. Yeah, I have cut the recovery part of the protocols to be able to do it in the time frame. But what's open in this field? Okay. Interesting question. So, so there is a trade-off between F and the latency, okay? In the sense that this protocol tempo is very fast, but you have small value of F or large value of F, it's not super efficient. So there is, it's the classical Paxos field where you have like Pareto optimum. So there is still some Pareto solutions that have not been found. For instance, how can you remove tail latency while tolerating F equal n over 2? Okay, for instance, minority of failures. That's a Pareto that has not been found. So some point for n equal 5, n equal 7, there are like tempo is optimum, Pareto optimum for this case, but like in the general case, we don't have solutions. That's a thing. An interesting avenue of research is also low averaging, for instance, blind writes. So when you don't have return value. So for instance, in blockchain, this is common to have this thing. So this is the motivation of egalitarian Paxos was that is to have optimal blind writes. So how can you extend this work to do that? Efficient reads also. They're like using the semantic of the application maybe is interesting. What we have tackled and have not presented here is partial replication, because we have a variation of tempo for partial replication. This is an interesting direction also. Yeah, question like that. Or open. Oops, sorry. You had a question, I think. Okay, so you could actually have a leaderless variation of Raft, but it would use Raft as a black box. So the protocol here, I did not present it the recovery part and the consensus part, in the sense that, yeah, it's a bit magical, but you need agreement, so you need consensus. So consensus, you need to solve it with Paxos or Raft. So like all of those protocols, they have some ballot mechanism, some consensus mechanism in them, okay? I did not present it the recovery part because we take one protocol and this is 2 hours long, okay? Because the recovery part is, of course, where the salt is, but it's absolutely non-trivial. So you can leaderless, create a leaderless variation of Raft. So you can use this approach to disseminate operations that are in the log of Raft, and then use Raft as a black box to store things. And when you don't have commutativity, when you have commutativity, you will be faster than Raft. That's the idea. So there is a paper by Oosterhout and SDI 2019 that is doing that. It's taking state machine replication and leveraging commutativity in a very modular way, in a very nice way. And they do it for, like in the PhD work of the student, they do it specifically for Raft. And so you might have a look at it. And in some sense, this is transforming Raft into a leaderless approach. But it's not completely leaderless because you don't construct, when you have conflict, you must use there is a single instance of Raft to compute everything. Whereas in this approach, you can have different consensus instances for different parts of the graph, you see? So it's the leaderless aspect it's not totally there, but it's a way to take Raft and make it faster when you have commuting operation.
Think of adaptive algorithms, for instance, Atlas and Apple, they assume fall down.
Okay, so adaptive. It's possible. You just need to reconfigure on the fly. So you just have reconfiguration, and you can remove some of the replicas during the reconfiguration phase. I don't think maybe it's challenging to do it smoothly, but strictly speaking, we have all of the tools to do it. So
This reminds me like the fast path, like fast Paxos, where you assume optimistically there are no failures, wait,
right.
timer expires,
Yeah. So yeah, it's possible to reconfigure. In fast Paxos, you do that too. So I mean, maybe when you're changing your configuration, you will have like a drop of performance, so you can try to do something better. An interesting thing also, so I did not present a plot about that, is that when things are commuting, if you have a crash, you can continue with the closest quorum because there is no leader. So that's a very interesting property of the system. So when you have a reconfiguration, maybe leaderless could leverage that in certain cases. But the thing is, it makes sense only if you have, I think, partial replication. In full replication, when you have a reconfiguration, basically it's a non-commuting command with everything. So if you have partial replicas, you reconfigure some of the replica that's possible, but not in the full replication case.
Adding a new nodes that do not nothing, they have no information. Do you live adding additional nodes? So how they will working through the tempo program? So they will start copy everything.
Okay, it's a reconfiguration problem. So you add on the fly new nodes. So basically, the state of the application, you have additional information, which is some metadata information regarding the system, and you create a command that changes this information that is non-commuting with everything. And then you need to have this command executed. And there are some conditions on the quorums between and after this execution, such that if new replicas take over, they are up to date, and you don't have a fork in the system. But it's something.
I don't understand when everybody has everything. So I don't get how you will save the time when I need to copy all replicas from all other nodes.
You mean how to catch up with the replica? So it's a separate problem in the sense that, for instance, if for instance I'm slow, there is this replica that is aware of everything, and I'm slow, I'm disconnected. How can I reconstruct the chain? Okay, so the idea is that you just ask the nodes, okay?
One by one.
You can, I mean, it's classical strategies in database system. You can ask in parallel, you can ask one by one. It depends on different things, but it's not something new in this class of protocol with respect to what is in Raft, for instance. It's the same technique. You would apply the same strategy. That is, I need to reconstruct. Instead of a log, it's a graph, but you need to do the same thing.
I need to rebuild the full graph, and then I would continue.
Exactly, yes, exactly. Okay, so it's 6 p.m. I think it's time to wrap up. Thank you very much.